And I would like to invite our first invited speaker, Jožef Ritonja from Slovenia, from University of Maribor. And the title is Electromechanical Oscillations in Power Systems, Analysis and Damping. So please.
Okay, Chairman, yes. No, it's good. Chairman, thank you for your presentation. Ladies, gentlemen, some friends, because here are also familiar faces from previous conferences. I will talk today about electromechanical oscillations in power systems. So during the presentation, I will try to answer on these two questions. So first question. So we all know that electrical and mechanical oscillation quantities oscillate in power system. So, but there is a lack of numerical assessments of these oscillations, and there are only skin deep knowledges about the correlation between these oscillations and parameters of power system. So this was the reason that we decided some years ago to start it with a study in this area. We were very afraid at the beginning, because we didn't know if useful conclusion even exists. So it was 3 years ago. Luckily, we obtained very good results. We obtained useful and important conclusions in the results about electromechanical oscillations, which are general and universal for different power systems. The study lasted 3 years. The results are new, are fresh, and I'm very glad that I obtained the opportunity to present these results as invited speaker on this conference. I really hope that these results will help professionals in this area by their work, and perhaps to motivate some of them to continue with our work. And the next question is how to damp this oscillation. Yes, we know all oscillations, especially mechanical oscillations, are never harmless. They can lead also to instability in the worst scenario, and how we can manage these oscillations, how we can control them. This will be the second part of my presentation. Darius showed us that we are here from different specialties, not only from electrical engineering, but presentation is very multidisciplinary. Therefore, I will make a very warm startup. Especially in the introduction, I will be very school-based. I will talk about the sources of oscillations, about consequences, about classification, and I will focus my presentation on one type of oscillations. Certainly, we need mathematical model for analysis and for control system design and synthesis, and this mathematical model will be presented in second part of presentation. The analysis of oscillations will be presented in third part, and in short part, how some control systems to damp these oscillations. I will provide summaries together with relevant chapters. This way, the presentation will be easier to understand, and I will skip the final joint summary, joint conclusions, to save some time, because I have so many things to explain, but only 45 minutes. So let's go to introduction. Where do these oscillations come from? So it is the most simple way to explain the principle of these oscillations, to observe the fundamental cell of power system. So power system consists of sources, of synchronous generators, of loads, of transmission lines, which connect all this. And the fundamental cell, or the basic unit of the power system, is is one synchronous generator which is connected to a transmission line to the other part. Here is other part of the power system. Here are many synchronous generators, and because there are so many and they have control system, the voltage here on the right bus is constant, voltage phasor, and the voltage phasor here on the left bus by synchronous generator depends on inputs of synchronous generator on mechanical torque and field excitation voltage. This fundamental cell is electromechanical system. Mechanical part is shaft and rotor. It is very simple to derive a simplified model of this part. We can do this in two stages. First, we can derive the mathematical model of mechanical part. Mechanical part is we just need second Newton's law 2 times to calculate speed of rotor and position of rotor. We obtain the speed of rotor from mechanical torque, from resultant of torque and integration of this. And after another integration, we obtain the position of rotor. So if we integrate the difference between speeds with mechanical rotor speed and synchronous speed, we obtained here we obtain rotor angle. Mathematical model of this mechanical part are 2 integrators connected in series. This model has 2 eigenvalues in origin of complex half plane. And another part, electrical part, these are windings. This electrical part produce electrical torque, and this electrical torque depends on the rotor angle. And this feedback in mathematical model means that the eigenvalues from the origin will move on the imaginary axis. And the imaginary part of these eigenvalues corresponds to the frequency of oscillations. If we will have here any disturbance, any changes in inputs or any deviations from steady state, this will result in oscillations. We can see these oscillations everywhere in all mechanical or electrical quantities, speed, angle. Here are some figures, so some results of measurements, secret measurements on real power plant. So we can see, so we have synchronous generator with locked controllers. So both inputs to synchronous generators, mechanical torque for turbine and field excitation voltage from excitation system are constant, but quantities in the synchronous machine oscillate. The frequency is not high. So we can hear from here to here, it is 5 seconds. You can see oscillation in speed in instantaneous 3-phase power. If you make zoom of the upper figure, so this is rotor speed more detailed. And if you make Fourier analysis, we can see that we have oscillation with one frequency with very high amplitude and some other frequencies with much lower amplitude. So these oscillations are here. What are the concept? Why are these oscillations today so important? Even more important than in past. So there are 4 reasons for this. One reason is that new synchronous generators are different from the old one because cost optimization, they are smaller, they have smaller damping findings, smaller moment of inertia, and also therefore smaller damping coefficient. Also, we have a lot of new devices in power system, batteries, solar plants, different, a lot of power electronics is inside. All these devices influence the oscillations. We have also many additional control systems in power systems. So in past, we just have turbine control, primary and secondary turbine control, and automatic voltage regulator. But now we have a lot of control loops to fulfill different requirements for environmental or economical or social requirements. And important is also that all people, so now is everywhere, so majority of owners of power system expected that the power system will operate very close or on the border of ultimate transmission capability. So it means there is no place for oscillations anymore. Consequences of these oscillations are clear: losses, shorter lifespan, reduced peak performance, and very important outages and blackouts of power system. I made short list of biggest outages in the world. So we can see the sad border, 1,000 million people without electricity was already reached 10 years ago in India. So blackouts happen everywhere, also in America, in Canada. They don't choose between rich and non-rich countries. Now, in these blackouts, these instabilities and oscillations are very close connected. They have very different forms. They are influenced by wide range of factors, and therefore there are many types of oscillations. I will talk only about one type of oscillation here. To explain which is this time, I have to talk a little bit about the classification of these oscillations. So all stability problems in synchronous generator can be divided into two disciplines. We will analyze rotor angle stability. It means the ability of synchronous generator to stay in synchronism after being disturbed. These disturbances could be larger or smaller. This happens not so often, very rarely, but small disturbances happen all the time. These are much more questionable. Therefore, we decided to analyze this type of stability problems, small signal rotor angle stability. Important for this type of stability problem is that in this case, we can use linearized model of devices in power system. This is very good, but this is possible because the exclusion of state spaces, all quantities are small. The responses of quantities which can lead to the instability are either aperiodic increase of rotor angle or oscillations. This is not problem anymore since the invention of automatic voltage regulator. This is not the problem. So the main problem are rotor angle oscillation with increased amplitude, which can lead to the instability, to stability problem. I already explained one of these rotor angle oscillations. It was oscillations of one synchronous generator against the other part of power plant. These oscillations are called local mode oscillations. But in power system, we have also other type of oscillation. We have also oscillation between more synchronous generators inside one power plant. These are intermachine mode oscillation. We have also oscillation between synchronous generator and turbine, or oscillation due to a control system. We have also oscillation between some areas in power system. But these are the most frequently occurred. And during my presentation, I will talk about local mode oscillations. Short conclusion of this introduction is that the most frequently encountered small signal stability problems are from the class of local mode oscillations, and the presentation will be focused on this type of oscillations. I will skip this slide. This is not a mistake. These are prepared for questions, if there will be any at the end. So, finite mathematical model. Is here something new? Can we just take this mathematical model? Yes, we can take it. There are many mathematical models, but the problem is if we can believe if they are accurate enough. This will try to explain in this second part. There are many mathematical models which describe behavior of synchronous generator, but unfortunately, the majority of this is not ready for analysis of electromechanical oscillation for small signal rotor oscillations. The reasons are that the model structure is not suitable because for small signal rotor oscillation, we will need linear analysis tools, and which majority of models are non-linear. And it is also very difficult to obtain all data parameters for some of non-linear models. So just a short survey of this model. The basic of all mathematical models for synchronous machine is the 7th order nonlinear DQ model. On other side, the most simple, this one, the first one is quite complicated. It's nonlinear, 7th order, and so on. But the most simple is voltage behind synchronous reactance models. These models are well known. But in the middle, we have many simplified models. These are some of them. There are really many, so it was really a lot of work in this area. But the most popular is the linearized 3rd order model. The best on this model that it has very good compromise between complexity and accuracy. This third order linearized model is derived from the 7th order nonlinear model. So the 7th order is basis. Both models describe this fundamental cell of power system. Therefore, I will verify, I will check if this 7th order nonlinear model is good enough for our analysis. So just short introduction. This model has 2 inputs like the fundamental cell, mechanical torque, and field excitation voltage. It has 7 state space variables, 5 electrical, 2 mechanical, a lot of equations. But the worst thing by this model is that if we would like to replace the measurement of the real generator with the simulation of this model, we need a lot of machine data. It is very difficult to obtain all this data. So to check how this model is good enough for our work, we prepare such laboratory equipment and make a lot of tests. Here is synchronous generator connected to network. Here is excitation system. Instead of turbine, we used induction machine with frequency converter. This produced mechanical torque, and field excitation voltage is coming from power amplifier, and we have a lot of measurement devices. All data which were provided by manufacturer are only these 8. But we need all these, so it was very time consuming to obtain all these data parameters. And here are results. So for small changes, if we make a small step change of mechanical torque for 5%, the PU, we obtained almost identical results. You can see black, red is measurement, and black are results from nonlinear model. So it means that the simplification by derivation of the model and not absolutely accurate measurement of parameters of the machine are small enough that the results are very good. So here are also results if we change field excitation voltage. So if we change voltage on rotor winding for 5%, almost, again, the results are almost identical. So we can use this model, but this model is possible only for numerical analysis, and therefore we analyzed this model first. We simplify this model. First, we reduce number of state space variables, and after then make linearization, and we obtained here are assumptions which are made for simplification, and we obtained 3rd order model. It has again 2 inputs, mechanical torque and voltage, but only 3 state space variables, 2 mechanical, 1 electrical, and only 9 coefficients. Here are equation of this model. 3 state space variables, 2 inputs, 3rd order. Here is the block diagram. You can see here that this model is the extension of the first simplified model, where we have mechanical and electrical torque, after then 1 integrator, and here was speed, and again 1 integrator, and here is rotor angle, and this feedback. but this model has also the damping and some electrical part. Because the model is of third order, it has 3 eigenvalues. 2 are most important. They are dominant, very close to imaginary axis here, and these eigenvalues are important. So some results. So we compare this linearized model with the nonlinear model. Again, small changes in mechanical torque for 5%, and you can see in this area of operation, the linearized model is give almost the same results as nonlinear model. Here are also results for field excitation voltage changing. So here is speed of synchronous generator, rotor angle, and voltage on the stator winding. Conclusion is that we can use this linearized third order model to make analysis of oscillations and also to later to make a design and synthesis of control system. Okay. Should we go to the third part of the presentation to analyze? This is the most important part, analysis of local mode oscillations. So what are the questions? So this is, I think, the most important. This is word to be careful. What is the question which we would like to answer? So first question is, what is the correlation between operating point of generators and local mode oscillations? So it means if we are operator in power plant and our generator operates by 10 megawatt and 10 megawatt, and we can see some oscillation, and these oscillations are weakly damped or even undamped. So what we have to do to increase the damping of this oscillation or to change the frequency of this oscillation? Should we increase the active power or decrease it, or something to do with reactive power? So this is the very important question for power plant operators, and this was our question. I will try to answer on this question during this presentation. And second question is, what is the impact of control system on local mode oscillation? So if we have synchronous generator, it has some local mode oscillation, and what will happen if we will add some of control systems? So I will focus here only on voltage control system, on automatic voltage regulator. So this will be the second question, and the third question is also very important, but I will not have time to answer on this. There are many potential users of these results, people from power plant to prevent activities that would lead to the instability, or for forecast planning of power systems, for forecast of local mode oscillation. What will happen if we will do something, if we will change generators, or if we will add some control system. Certainly also the third part for people who are working in the area of the automation system, and the job is design and control of the design and synthesis of power system stabilizer. And this knowledge here will be also possible if we will have measurements of power in power system, and we will see a lot of oscillation, and we will not know which of these oscillations are local mode oscillations. So there are many proposals, many potential users. How is the previous work in this area? So very bad. So we have some studies we can find some studies in literature review. First time they start with work in this area 60 years ago. The topic is still very up to date. You can see this is very cited paper from year 2017, but there are no correlation about parameters and oscillation, and we can here also we cannot see any numerical assessment in this paper. Here, the only papers when we can find numerical assessment are these two. One is 40 years old, and we can see the estimation of control frequency oscillations and torsional oscillations. And after then, this is 30 years old paper. We can see here we can find the estimation of local mode oscillations and inter-area oscillations. But since then, the power system changed. So therefore, we really need new assessment. And it is also one thing very important. In this paper, we can find only estimation about oscillations frequency and nothing about damping of these oscillations. So how we can come to these conclusions? We will use eigenvalue analysis. And for this analysis, we will use third-order linearized model. With this analysis, we will observe eigenvalues of this third-order model. We know there are 3 eigenvalues. It is very simple to calculate this. Third-order model is simple. It has simple system matrix A, and we just calculate characteristic equation and calculate eigenvalues. And we obtain 3 eigenvalues, 2 complex. These complex are important because they describe local mode oscillations. So these are these complex eigenvalues, real and imaginary parts, sigma and omega, and they correspond to the local mode oscillation. So real part denotes the decay of amplitude, so it denotes the damping, and imaginary part denotes the frequency of this oscillation, or more precise, the frequency, the natural frequency or eigenfrequency we can calculate with this equation, and damping ratio with this equation, very school-based. Our procedure was very simple, but very time-consuming. We have to obtain machine data for more 100 synchronous generators. And after then, we select operating point. For this operating point, we calculate parameters of linearized model. After then, calculate eigenvalues. And from these eigenvalues, calculate frequency and damping. And after then, we repeat, we select other operating point, and so on. So here are the results for first generator. It is hydro-type synchronous generator with nominal power 9 MVA. Here are the data, machine data. And we change active and reactive power in the area from 0 till 120% of nominal power. So we are going also in the overload area. So we do the same for active and reactive power. And here are the results. This is the most important part. So first we take active power, we set active power 0 and reactive power 0. So the synchronous generator is idle, and we calculate eigenvalue. Is this somewhere here? If I zoom this area, this eigenvalue is now here. You can see this is only this peak diagram is only this part. We can see imaginary part is from 5 till x is till 11, and we are on the left, in the left half plane. So imaginary axis is somewhere here. So after then we keep the same reactive power, and we increase the active power, and the eigenvalue moves. It is somewhere here, somewhere here. If we put by the same reactive power 0, nominal active power, our eigenvalue is here. This is for nominal operating point. And if we increase till 120%, our eigenvalue will come here. So this curve corresponds to the constant reactive power, Q is 0, for changing active power. And after then we increase reactive power to 0.1, and we keep this constant, but we change active power from 0 to 1.2. Very interesting results. So if we increase Q is going here, and arrow for P is this one. First question is this only valid for this generator, or is this valid also for bigger and smaller, or is this valid also for turbo type generators? So we test it. We make test with hydro type generator, and we obtained very similar forms of curves of eigenvalues. So you can see 12 MVA. So here I will show only some results. There are many, more than 100 generators, 158, 615. So we can conclude that by all generator, the dependencies of synchronous generator of eigenvalues is very similar for all hydro type generators without any controller. So this is our first conclusion. The form of these dependencies is such for all hydro generators. What else? You can see that increase of P results in better damping because we are going far from the imaginary axis. We can also say that increase of Q results in higher frequency of these oscillations. And we can also see that the stability high problematic area, so where the oscillations are low damped, is this one here, by high values of active power and low high values of reactive power and low values of active power. And stability low problematic area, so where the system will be very good damped, is here, where we have by high P and low Q. So it is very good answer. If somebody is operating, so some binomial operating point somewhere here, and the system starts to oscillate. So if it would change, so increase damping of oscillation, what he has to do, reduce the reactive power and increase the active power. This is important conclusion. Is this valid also for turbo type synchronous generators? So we just take the data and check it. So this is one turbo type generator, 25 MVA. Here are data, and here are first results. They are not the same. You can see if I compare, so because we forgot, these were results before for hydro type generator, and these are the results of turbo type generator. We can see that the form of these curves is not the same. It has this increased part top here, this part. And if we calculate also for other turbo type generators, we can see that this is everywhere. By all turbo type generators, we have similar shapes. Here are some figures together. So always we have such shapes. And our conclusions for this type. Again, all turbo type generators have similar dependencies of eigenvalues from P and Q. By increase of Q, the result is, the conclusion is the same, higher reactive power, higher frequency. But it is not possible to tell what will increase the damping of the system of local mode oscillation. We just can say something about areas. Low damped area is here when we have high Q and low P, and high damped area where there were the smallest stability problem is here when we have high active power, very high active power, even overload, and low values of Q. These are conclusions for generators without any control system. But when we equip this generator with, so it is very interesting, what does the transmission line, if we change the transmission line, if this is valid and so on. And these questions are very important. All of these questions are answered in the study. But during the presentation, I will just tell, because these results are very interesting, what do the control systems make with these oscillations? So I will focus on automatic voltage regulator because all synchronous generators in power system are equipped with voltage control system. So again, I took the same hydro type synchronous generator, but now I equipped, I will show it, so with controls, with voltage regulator. So I will measure, you can see here, voltage and compare it with reference stator voltage, and using this automatic voltage regulator and excitation system, I will change the field excitation voltage. So I only add this part to the previous model. Due to additional this part, we have 4 eigenvalues. Again, 2 dominant complex are the most important, and here are the eigenvalues of this fundamental part, fundamental cell with automatic voltage regulator. It is very surprising. You can see before, when we increase the active power, we got better damping. We are going here in this area, left from the imaginary axis, more far in the left half plane. But now if I increase active power, I will reduce damping and I will also come in unstable region. So here is imaginary axis. So if I compare these 2 figures, left one, the same generator without voltage control system and with voltage control system. So it was very surprising for us. We tested, we checked this many times. We tested with different synchronous generators, and we saw that always by hydro type synchronous generator, we have this phenomenon. So always if we increase P, the damping will decrease completely. So this is the consequence of introduction of automatic voltage regulator. Very danger supplementation. So it is the same for different sizes of synchronous generators. So, and if we make a conclusion, again, we have similar curves, similar loss size, but this is new. Increase in active power results in decrease because we are going right. If we will operate till nominal operating point, you can see we will stay in stable left half plane. This square here denotes nominal operating point. But if we will overload synchronous generator, we can also go into the unstable region. Another conclusion is that Q again increase the frequency of local mode oscillations, and the stability high problematic area is when we will have high value of active power and low Q. This is the especially danger, and the stability low problematic, the best damped part of the operation is here by low P and low Q. So this is for hydro type synchronous generators. How is it turbo type? Not so. So we can see in this case, if we increase active power, the system will not, mainly will not go to the right half plane of the complex plane. So if we will increase P, we will go from here, we will go left far from imaginary axis. Just to compare both figures, left one, the previous one for hydro generate. No, this is the left one is for turbo type without AVR, so on, higher P, better damping, and here with AVR, it is not so bad. We are also going to the left side, and only in some special cases, we will go right in the unstable half plane. So we can check this also with different sizes, and everywhere was the same shapes. And the conclusions are, again, The dependency of eigenvalues is similar by all analyzed generators. Increase of P results mainly in increase of local damping. Only in special cases I will go such far into unstable plane. Increase of Q means increase of frequency. Stability, high problematic area is here if we have extreme high value of P. And stability, low problematic area is here when we have low P and low Q. These are very important conclusions. We would like to test, to verify these conclusions also with experimental results. We use the same experimental system as before, the same synchronous generator with this data. And we set operating point from this area. And after then we make a small disturbances and try to estimate the damping and frequency of these oscillations. Here is operating point 20. So high value of active power, low value of reactive power. In this case, without control system, we expect that the system will be well damped. Yes, because so it must be well damped. So, and if we change mechanical torque from 11.5 till 13.5, so we obtain such oscillations. Black are the results of measurements, and red is the approximate identification of the model. So we identified third order model, and from this model is calculate the eigenvalues. So this is other operating point where the active power is small and reactive power is high. In this case, the damping must be smaller and the frequency higher. It is true. So, okay. We made this for different operating points, calculate eigenvalues and draw it here. The blue one dotted line means the calculated from the mathematical model, third order model, and the red one points means the estimations of eigenvalues from measurements. We can see that this that our conclusions from a linearized model agree with the measurement on real object. So we were just to remember, it was turbo type generator, it was very fast, and we obtained similar dependencies. Okay, the here, and now some words. I told that this part will be short. How we can damp these oscillations? What are the solutions for damping these oscillations? Yes, we can change the synchronous generators to make the construction as in the past. This is certainly not the best solution. Or we can add additional control system for damping. This is so-called power system stabilizer. This is nothing so new. We can already buy power system stabilizer. There are as optional in excitation system of different producer, but unfortunately the majority of this power system stabilizer is very ineffective. So we made a study 10 years ago, but now is not, there are not many changes now. So in Slovenian power system, we have only a quarter, approximately a quarter of power system, a quarter of all synchronous generators were equipped with operating power system stabilizer. So what is the reason? The main reason is that commercial power system stabilizer are based on very old linear concept, which is not successful to damp oscillation of non-linear synchronous generator. Also, therefore, the tuning is very complicated, very time-consuming, and if we succeed to find the optimal parameters for nominal operating point, these parameters will not be good for some other operating point because of non-linearity. The conventional power system stabilizer we make in such way, we have to make synchronous generator with connected line. Here is voltage control system, and we just have to measure active power or speed sent to the transfer function to do this controller. It is described with this transfer function, very simple. Here we have anti-aliasing filter, washout filter in some lead-lag terms, and the output from controller is added to the reference terminal voltage. And yes, it is clear that such simple controller will be not able to control such complicated nonlinear control system. Therefore, almost all advanced control theories were used to improve power system stabilizers, almost everything what we can get in the area of automation control. I think the most promising methods are adaptive control and robust method, or Trump. So we bet on adaptive control. We think that this is the best solution for this, and because there are many adaptive control theories, especially on modular reference adaptive control. I will show some results. So we have a lot of results with derivation of such power system stabilizer, of adaptive power system stabilizer. Here are some simulation results. So with simulation, we always get good results, but these are excellent. So this is the inputs. These are the inputs to synchronous generator. We change mechanical torque and the reference terminal voltage. We have different shapes of changing sinuses and step changes. And these are the responses of model. Look here, after 15 seconds, I will change the mechanical torque, and this is seen here in the oscillations of active power and rotor angle. This is in nominal operating point with our adaptive stabilizer. In nominal operating point, the behavior is perfect. And what is the most important, if we use the same adaptive, with the same parameter, the same structure, adaptive stabilizer for any other operating point, also for operating point in unstable region, where the active power is 25% over the nominal point. So we obtain almost the similar results. Some experimental results. So we made these experiments on one other synchronous generator, a bit bigger. So instead of induction machine, we have DC motor for generating mechanical torque. Excitation system, some filters, and this space for realize the AVR and PSS algorithms. This is synchronous generator, DC motor, this is electronic, and this space, and here are results. So almost in the entire operating range, this is step change of mechanical torque. This produce these oscillations without stabilizer, but with stabilizer, these oscillations were really good, damped in entire operating range. Some conclusions. Yes, it's clear conventional power system stabilizer is not sufficient. Adaptive and robust stabilizer are very perspective concepts. We have already some results, simulation experimental results of such adaptive stabilizer. But what we can see when we look out from our laboratory, we can see that there are a lot of work in this area, very groups with people from industry, who developed the stabilizers, from research institution and from power plant are working together. So this problem is very up to date. We expect that in 10 years, a new advanced concept will go in the realization of power system stabilizer in commercial products instead of the conventional linear one. And it is very challenging now to predict which of the presented concepts will prevail in the future. this is all from my side. Once again, thank you for your opportunity and for your to be here. Yes, thank you.
Thank you. Do you have any questions about the presentation?
Hello, my name is Audrius Baranauskas from Litgrid, Lithuanian TSO, and I have two questions or comments. First of all, concerning your eigenvalue analysis, you showed that you make a different calculations of eigenvalues when you change the reactive power from 0 to 1.2 per unit. Have you also tried to make a calculations when the generators consume the reactive power?
Yes, this is a good question. Yes, we made calculation for capacity of inductive operation, but because there is nothing so revolutionary. So in this case, but because it is much more important to operate in with such a power factor, so therefore I showed only this result.
Okay, but conclusion could be confirmed as well with the consumption of reactive power, because in Lithuania, for example, our generators almost always consumes reactive power instead of generating. It's really high voltages in our system.
Okay. It will be not fair to explain the conclusion now. We made all these tests very similar, but really try to remember. By active power, it is the same. So we increase the active power. So I am talking about the synchronous generators without control system. So as the first part of the presentation, the active power, the influence of active power was the same. If you increase the active power, also the damping will increase. But by the increase of reactive, I really cannot say this really, because it is so far ago. So I could check it. So,
okay. And maybe second comment or question, you mentioned that the battery is increasing in power systems. We also develop few projects in Lithuania to install the batteries. So you mentioned that the batteries reduce the damping or at least they have an influence on oscillations. We see the batteries as a tool to damp the oscillations. Maybe you will have also made some investigation concerning this.
Yes, we also made some investigation in this area, but because this is very up-to-date question. But we have to know two things. First, the source of oscillations are synchronous generators. So, and it is the best way to put the stabilizer near to this source. Therefore, the synchronous generator station system is very good. It's very good device, very effective device to damp these oscillations. If we have batteries close to the source of this oscillation, then they could be sufficient, but in other case, no. The implementation of batteries is already, this is not so, there is already many results in this area. I'm sure you remember the first battery which was used for implementation was in this 10 megawatt battery in South California and Chino substation. This is the most cited paper. It was in year 88. So they used the batteries. They showed that it is possible to damp this oscillation, but for damping of local mode oscillation is, I'm still sure, the best way, the cheapest way, and the most effective way, just to use excitation system of synchronous generators.
Stabilizers.
Yes, the conventional such power system stabilizer installed in the excitation system.
Maybe for the whole power system, it's really dangerous to have wide area oscillations, and maybe batteries could help in this area to damp the wide area oscillations between the countries.
Yes, for other parts, yes, I believe for other parts, other types of oscillations, the batteries should be very successful. I think, yes.
Thank you.
Thank you for the question. Yes.
Okay. So if there are no questions. If there are no questions, so I would like to thank you to the presenter. And we have some special gift, the invited speaker. You probably will enjoy after your presentation.
Yes,
Okay,
I'm
thank
sure.
you.
Oh, yes.